All right, so some of the stuff that we did in 5.1 was like a very, very introductory idea to this area under the curve. And this first line kind of sums it up. We talked about the left hand Riemann sum, the right hand Riemann sum, the midpoint Riemann sum. These aren't just random values that we are trying to estimate or figure out. They're actually supposed to be leading us to the true area under the curve. So the left, the right, and midpoint are all approximating the exact same thing. Obviously, they're going to show up different because we've got different left endpoints, right endpoints, midpoints. But the best part is, and this is this next paragraph, the wonderful thing is if f is continuous, the limit of all the Riemann sums as n approaches infinity. So let's explain what that means. Remember, n is the number of rectangles. So, 4 rectangles might be a decent approximation. 10 rectangles would be an even better approximation. 25 would be even better than that. And you can kind of get a visual. The thinner the rectangle is, the more of them you're going to have, the more accurate it's going to be. So 2 different things. You could either consider the number of rectangles as going to infinity, or you can consider the width of the subintervals going to 0. Whatever way you look at it, the limit of those as n approaches infinity is the real actual value. So the more rectangles you add, the more closely it's going to approximate what the actual area under the curve is. So this actual area under the curve, this is called the definite integral of f. Okay, so the definite integral of f from a to b, f being the function and then from a to b being the interval, which is denoted, so we've got this kind of crazy notation here. I'm going to do my best to walk you through it. So there's our integral sign, and then we say from a to b. So this is a little bit different. We use the integral sign when we were talking about antiderivatives, but this time we've got these limits that we put on the integral sign, from a to b. So this is the lower limit, this is the upper limit. Those are just the endpoints of the interval that we're talking about. Of f of x, we've seen that there before, and then dx. Okay, so let me write all the pieces on here. So this guy right here, we still call that the integrand. And we've been using that notation for a little while now, especially when we were talking about the antiderivatives. And then these two pieces, the a and the b, these are the limits of integration. So this notation, even though it looks very similar, this makes it a definite integral. Okay, so now this part is a little bit weird. This is the definite integral. Here's what it's defined as. It is defined as the limit as n approaches infinity. That's what we were talking about up here. So the definite integral is the limit as n approaches infinity of the Riemann sum. Okay, so this next notation is going to be very, very strange. I'm going to walk you through it. So the limit of, now we start with a sum. This is a Greek letter epsilon. It stands for sum. So what we're doing is we are going from the first rectangle. So we start with I equals 1, meaning the first rectangle, and then going up to n, the nth rectangle. So this means the sum from the first rectangle to the nth rectangle. So either from the first rectangle to the 5th rectangle, from the first rectangle to the 20th rectangle, whatever it is. And then the Riemann sums, remember, represent rectangles. The rectangles are width times height. The height of the rectangle was given by a function value. So we'd say f of c sub I, and then times delta x sub I. So all this stuff is going to look very, very weird. Like I said, I'm going to explain it. So this right here, this notation means we're taking the sum, and it's the sum of all of these rectangles, and that's exactly what we were doing yesterday. We did the sum of the first, first rectangle plus second rectangle plus third rectangle, etc. This represents the height, and remember the height of each rectangle is given by a function value, and so we'd say the function value at c sub I is just whatever height we choose for the I rectangle. If it's the first rectangle, the second rectangle, the third rectangle. And then delta x is a little change in x, and change in x just represents the width. Okay, so as crazy as this notation is, basically what I want you to remember is that these two things represent each rectangle. It's the height, which is given by a function value, times the width, which is given by a little change in x. Maybe the change in x is 2/5, like we saw yesterday. Maybe the change in x is 1, like we saw yesterday. But either way, this represents the area of one rectangle. This is all the rectangles summed up from 1 to whatever. And then this is the limit as n approaches infinity. The larger the number of rectangle gets, the closer it gets to our definite integral, which we have right here. Okay? So, theorem here, it's pretty quick and easy. If f of x is continuous, or if f of x is continuous with at most finitely many jump discontinuities, meaning, yeah, sure, you can throw a couple jump discontinuities in there and it won't mess us up. Then we say that f of x is integrable. It's a very clumsy word. No one sounds good saying it, I promise. Over the interval from a to b. So it's basically the same idea as differentiable. Differentiable means we can take the derivative. Integrable means we are able to integrate it, or we are able to take the integral. So we're going to talk about this definite integral as signed area. Yesterday, or in the last lesson, we talked about how we really only use the positive area, the area above the x-axis, and then we're going to transition into seeing everything. So when the function is above the x-axis, that's what this means right here. The definite integral defines the area between the graph and the x-axis. Okay, so the area between the graph and the x-axis. And just for comparison's sake, I'm going to show you something that we did yesterday. Okay, so we talked about, for instance, this definite integral is what we were approximating, and it represented the area in between this parabola and the x-axis. That's what we were trying to approximate. All right, if we didn't cut ourselves off at the x-axis, it could keep going down forever. Quick note, very important thing to consider. Anything below the x-axis, we consider this to have negative area. I know, speaking from geometry, we're not used to negative area. We're told that it's not really a thing, but in calculus, it is. All right, so regions below the x-axis are considered to have negative area. Okay, so in case you're wondering what happens if the function dips down below the x-axis, which most functions do at some point, you consider it to be negative area. Okay, so when we're talking about the signed area of a region, if we want to know, what the area above the x-axis is, what the area below the x-axis is, the signed area, we take the area above the x-axis and then subtract the area below the x-axis. And I'm going to explain what that means in just a couple examples in terms of velocity. All right, so using signed area, we can say this. The integral from a to b, which is the notation we have up above, it's the signed area of the region between the graph and the x-axis. Okay, so signed area, meaning if it's above the x-axis, we count it as positive area. If it's below the x-axis, we count it as negative area. On the next page, we'll see a specific example of that. All right, so signed area, that's how we define the area from A to B. It's the area between the graph and the x-axis. If it's above, we count it as positive. If it's below, we count it as negative. So looking at these next few specific examples will really help to kind of clear that up for us. Okay, so this next chunk of problems, we are going to be using geometry to find definite integrals. So area, the first way that we discovered area is by using some of these geometric formulas, rectangles, which we talked about the last couple days, triangles perhaps, trapezoids, we'll even see semicircles at some point, but mostly like rectangles and triangles are what you can expect. All right, so example 1. First, let's talk about exactly what this notation is asking us for, and then we'll set up how to figure that out. So when we have the definite integral from 2 to 5 of this function right here, what we're trying to figure out is the area under this curve between 2 and 5. And so the best way to tackle this is to set up a picture. Okay, so let's set up a picture. We're going from 2 to 5, so if you're looking on your x-axis, we've got 1, 2, 3, 4, 5. The best way to get an accurate picture, of course, is to know where this function is at 2, where this function is at 5. So if we plug in 2, f of 2, we have 2 times 2 plus 1, so that is 5. So let's go up by 2's here. 2, 4, 6. So right there is the point 2, 5. Then if we plug in 5, 2 times 5 plus 1 is 11. So 2, 4, 6, 8, 10, and 12. So at 5, we're up here at 11. Okay, so here's our function. This is the only part we care about right here. Okay, so this is what we're trying to find. Here's our function, 2x plus 1. So that's this line right here. We are going from 2 to 5. And it's very important that we know the heights of this function. Okay, so at 2, the function height is 5, and then at 5, the function height is 11. Okay, so that's going to play into our geometry. So what we're trying to find is the area between the curve and the x-axis. So we are trying to find this area right here. So luckily for us, that's trapezoid. We have a formula for the area of a trapezoid. Or if you forgot that, or you don't like trapezoids for some reason, you could always split this up and make it a rectangle and a triangle. That definitely works as well, but the trapezoid is just one formula that you can use. So we use A for area, and the area of a trapezoid, I will give you this right now. Area of a trapezoid is 1/2 plus the sum of the bases times the height. Okay, so for this trapezoid, we're going to kind of consider it to be like on its side, like this. Okay, so we consider this to be the height, and then we say base 1, base 2. All right, so just so you know, that is how trapezoids work. So we've got 1/2, that's just part of the formula. Sum of the bases will be 5 plus 11. And then times the height will actually technically be the width here. So from 2 to 5 would be 3. All right, so that's our area formula. We plug that in. 5 plus 11 gives us 16. Half of that is 8, times 3 is 24. All right, so the definite integral from 2 to 5 of 2x plus 1 ends up giving us 24. And again, what that represents is the area under this curve, or I guess between this curve and the x-axis from 2 to 5. Okay, so that's one where our function is entirely positive between 2 and 5. The next couple that we're going to look at, we have some negative spots, so we'll talk about what that means. So example 2, we've got this piecewise function. So let's get a picture of our piecewise function first. So x takes us from 0 to 5. Okay, so we're going all the way up to 5. And then they give us these two different functions. So x minus 1, we are going to have right there, x minus 1, and then we're going to have a slope of 1. So we go from here to here to here, and one more to here. So it only goes from 0 to 3, and then these are both closed endpoints, so we are going to have closed circles here. So there's the first part of our graph. And then from 3 to 5, we do 8 minus 2x. So if I plug in 3 into 8 minus 2x, I actually pick up right here. I have a height of 2. And then for 5, I have a slope of negative 2. So I am going to go down 2 over to the right 1. I'm going to go down 2 over to the right 1, and my graph will end right here. Okay, so that's my graph. That's what I'm looking at. I've got the first piece of my piecewise function, second piece of my piecewise function. We are going to evaluate these two things right here. So for part A, we're going to evaluate from 0 to 3, meaning we want the area under the curve from 0 to 3. So here's 3 right here. So the area between the curve and the x-axis. So we want this area right here. Now remember what we talked about on the previous page. This area right here, we consider it to be negative area, and then this area we consider to be positive area. So whatever formula we use, we consider this to be a negative area that we're going to combine with this area right here. Okay, so to evaluate this, we've got the negative piece, so 1/2, and then this is just, base times height. So the base takes us from 0 to 1. So that, of course, is 1. And then for the height, this is how you can bring the negative part into it. This function goes from 0 to -1, so we can sort of consider it to have a height of -1. Comes off the function value on the graph. That's how you end up getting that -1/2 as the area of this triangle. Because again, when you're below the x-axis, you consider it to be negative area, not positive area. Okay, and then plus for the next piece, this positive area is another triangle. So 1/2. The base of this goes from 1 to 2 and 2 to 3. So that is a base of 2. And then the height, it reaches a high value of 2. Okay, so we plug that in, simplify it down. This ends up giving me -1/2 and then plus 2. So overall I have I have a definite integral of 3/2. So if I took this area, this is the signed area, where this piece right here actually kind of cancels out this piece right here. So 3/2 is just this area that hasn't been canceled out. So I want you to think of this in terms of position, velocity, and acceleration. If this function is considered to be your velocity, what we're technically trying to find here is displacement. All right, so if I have this velocity right here, that means I'm moving backward, then I'm moving forward. Here, the amount that I moved backward kind of canceled out the amount that I moved forward, and then all I'm calculating is this area right here, and it leaves me with 3/2. So any time that you are moving backward, it's going to cancel out any forward movement that you have when you're trying to calculate displacement. The same thing works here. This backward movement cancels out the forward movement. That's why we have to consider this to be negative rather than positive area. All right? The next one, we're going to go from 0 all the way to 5. So we already covered from 0 to 3, so I want to take this the rest of the way up to 5. Okay, so now I've got 3 different triangles that I'm going to calculate the area of. These ones come out negative, and this one's going to come out positive. Okay, so I already know that first one. It's this little negative piece right here. Now this one I have to recalculate. So 1/2, its width is 1, 2, 3 units, and then its height is still 2, just like it was up above. And then plus, now this very last piece, I have 1/2, its width is 1, and then its height goes down to a -2, so we're going to use that -2 as its height. Okay, and that way we end up with a negative value. So this is a -1/2, plus, this gives me 3, and then this gives me a -1. Okay, so I've got 1/2 plus 3 minus 1. This actually also gives me 3/2, which seems kind of confusing that if I go the rest of the way I'd get the same area. But if you look at this, here I've got this area up to this point right here. Then I have a positive triangle and a negative triangle that are the exact same size. So it's kind of like I moved forward but then moved backwards the same amount. So it's like I'm right back where I started if we're talking about displacement. All right. Example 3 and 4, we're just going to very quickly talk about signed area, meaning what would be above the x-axis, what would be below the x-axis. So sketch the signed area represented by the definite integral from 0 to 3 pi of sine x. So we know the way that sine works, which goes from -1 to +1, and then we're going from 0 to 3 pi. Okay, so let's do pi, 2 pi, and then 3 pi. So our sine function, remember it starts at 0, 0. It goes up to 1, back down to 0, down to -1, back up to 0. That's one cycle of sine, and then it's going to go through another half cycle before it comes back to 3 pi. So not the greatest sketch in the world, but it's going to look something like that. So when we're trying to get the definite integral from 0 to 3 pi, it means we want the area between the function and the x-axis. So 3 different areas right here. So indicate the regions of positive and negative area. Well, this whole hill right here, you would calculate this as positive area, and then this little valley, because it's below the x-axis, you would count it as negative area, and then this little hill would be positive area. Okay, so that's literally all I'm asking you to do is indicate the regions of positive and negative area and just sketching what this area would look like. Okay, so if we were to go a step further and actually get this, which we can't because these aren't geometric shapes, so we don't actually have the capability of doing this quite yet, what would happen is this shape would actually cancel this shape out, and it would just end up being this area right here. All right, but more about that in a couple lessons. Okay, last one for right now is the sign of the integral of x cubed from -2 to 1. Determining the sign without calculating it basically means what sign is going to end up taking over for our final answer. Is there going to be more negative area? Is there going to be more positive area? Because remember, equal area of negative and positive end up canceling each other out. Just like these two pieces would cancel each other out, just like these two pieces cancel each other out, and these two pieces cancel each other out. This one, for instance, ended up having an overall positive area from 0 to 5 because these pieces canceled each other out, these pieces canceled each other out, and I had a positive area remaining. That's why my overall area was positive. So let's get just a very general sketch of x cubed. Looks like this. Okay, and if we want to take the area from -2 to 1, okay, so it looks something like this. We want to calculate this area between the curve and the x-axis. So you've got area here and area here. Now here's what's going to happen. This is a negative area down below the x-axis. This is a positive area up above the x-axis. If you look at these two pieces, this little negative piece is going to cancel with this little positive piece, leaving us with all of this. So overall, the sign will end up being negative because there's more area below the x-axis than there is above the x-axis. So the only answer we're looking for here is the word negative, just showing that that negative area is kind of going to overtake the positive area. All right, so we've done everything we can do in terms of the geometry that we already know, and we talked about doing Riemann sums. So as we move more into definite integrals, we're going to get better ways to get the area of curves like this that don't just fit into perfect geometric shapes. All right, so that's it for now.